In this video, we're going to look at inverses of permutations inside of Sn. If alpha is given in two-row form, so we have alpha has two-row form that looks like this, I1, I2, I3, all the way up to In, then it turns out that alpha inverse can be written as, just swap the rows. I1, I2, I3 becomes the top row, and the bottom row just becomes 1, 2, 3, all the way up to N. And it's pretty straightforward that if you've got this and if you compose the two permutations in the form first do alpha, then do alpha inverse, we would have this and this and when we start doing our tracing algorithm, and I want to have a two-row form that I'm going to basically start with 1, 2, 3 all the way up to N. Let's see, let's make that a little bit more compact. I am eventually going to want to get to an arbitrary k, and it continues on up to N. And the tracing algorithm is simply going to look like, well, 1 goes to I1, and I1 goes to 1, so 1 goes to 1. And then we're going to have 2 goes to I2, and I2 goes to 2, so 2 goes to 2. And 3 will go to I3, and I3 goes to 3, and so we wind up eventually getting over here to k. K will go to ik, and ik will go back to k, so k will go to k, and then finally we wind up with n goes to in, and in goes to n, so we wind up with the identity permutation. You should stop the video and you should look at alpha inverse followed by alpha, and you should be able to show that that is also equal to the identity. So go ahead and stop the video and do that for a minute. Okay, so hopefully you've stopped the video and you've found this out, but this is how you would go about showing that this particular thing actually is equal to E. Again, it's just our tracing algorithm, but this time we're going to start with I1. I1 goes to 1, and 1 goes back to I1, and so we can write that as I1 goes to I1. And in a similar fashion, I2 will go to I2, and all the way up to In will go to In. In particular, if we just look at any of them, Ik will go to K, but then K will go back to Ik. And it's important to realize that this particular permutation sends Ik to Ik for k equal 1, 2, all the way up to n, and hence this is indeed the do-nothing permutation. So this is indeed equal to E. Well, we have two different ways of writing permutations, so I want to look at inverses in disjoint cycle decomposition as well. So if alpha is written as just a single cycle, A1 goes to A2 all the way up to AK, well, what this basically means is that alpha is sending A1 to A2 and A2 to A3 and AK minus 1 to AK, and AK back to A1. So to get alpha inverse, we need to just run around the cycle in the opposite direction. So this will say that alpha inverse is actually equal to A1 goes to AK, which goes to AK minus 1, which goes to AK minus 2 until we eventually get down to A2, which will go back to A1. And if we look at the composition of this pair of permutations, the symbols, of course, would look like this. And when we actually do the composition, let's see, A1 is going to go to AK, and AK goes back to A1. So A1 is just going to be a single one cycle. And then AK minus 1 goes to, rather, AK goes to AK minus 1. Well, AK minus 1 sits here. And so AK minus 1 goes back to AK. So AK is a single one cycle. And if we continue, we find out that AK minus 1 is a single cycle, and all the way down to when we get to A2, A2 goes to A1 in this one, and A1 goes to A2, so A2 goes to itself. And since this is just a product of one cycles, that's known to be the identity permutation. If we do the composition going the other way, you get the exact same result. You ought to stop the video and you ought to compose this for yourself as well. So hopefully you stopped the video and hopefully you did the composition. This composition is going to look like this. And A2 is the last one there, and A1, A2, and we get to AK minus 1 and AK. And in the tracing here, we start with A1, who goes to A2, and A2 goes back to A1. So we have A1 is a single cycle. And when we look at A2, A2 is going to go to A3, but A3 is going to sit right here, and A3 is going to go back to A2. So A2 is going to be a single cycle. And this is going to continue all the way up until you finally get to the end of this. AK minus 1 is going to go to AK, and then AK goes to AK minus 1. So AK minus 1 is fixed. And then finally, AK goes to 1 under this particular permutation, and A1 goes to AK under that one. And so here again, what this means is that AK is a one cycle. And so again, we wind up with a product of one cycles. And products of one cycles mean that they fix everything, and hence we have E. Well, the last thing we need to do is generalize the inverse of a cycle to get inverses of permutations that are written in disjoint cycle decomposition. So if we have alpha is written as, say, delta 1, delta 2, all the way up to delta L, where the deltas are disjoint cycles, then it turns out that to get alpha inverse, all you have to do is reverse each one of the cycles in turn. It's also important to realize that you can reverse the order of these because they are disjoint permutations, and disjoint permutations commute. So just as a real quick example, if I have alpha is equal to, say, 1 goes to 5 goes to 8, and then 2 goes to 3, and 4 goes to 7 goes to 10, goes to 12, and this is living inside S12, well, first of all, it's important to realize that, yeah, this is disjoint. No symbol appears in more than one of these. And as a consequence, we can write alpha inverse is equal to 185, 2, 3, 4, 12, 10, 7. Or we can turn that around and write it as 4, not 4, 7, 4, 12, 10, 7, 2, 3, and then 1, 8, 5. And that is it for this particular video.